This is DC Electricity Part 2, Circuits with Resistance. In this video we look at the current voltage characteristics of resistors, a thin copper wire, a filament lamp, diode and a light emitting diode. It also includes sample exam questions. First example is a simple resistor. This is the circuit I use to measure it. Current voltage characteristic of a component is a graph of voltage against current. This is a photo of the circuit that I use and this is the actual circuit. Here are the results. If you want to see them properly, pause the video. The graph looks like this, a nice straight line, and that means that it's ohmic. Conductor is obeying Ohm's law if the voltage is proportional to the current at a constant temperature. That means it's got to be a straight line through the origin, and if you ask what Ohm's law is, you must include the clause about temperature. It's not a mark-worthy answer. The gradient of this graph is I over V, which is conductance, so the reciprocal of resistance. You can work out that the current is 16 times 10 to the minus 3 amp, and the voltage is 2.34 volts. Gives a conductance of 6.83 millisiemens. If you do a reciprocal of that, the resistance of 146 ohms. This is the actual resistor I use, and it's brown, green, brown pattern. Says 1, 5 and then 1, 0, 150 ohms, and that's within 5% of the value I got. Second experiment is the current and voltage characteristic of a thin copper wire. This is the circuit I used. This is the circuit diagram. Connecting a wire across a cell shorts it. Very big current flowing for a very short amount of time. Everything in the circuit gets really hot. Ohm's law is violated. Remember that temperature clause that I said you must include in an A-level physics answer. What I did in this case was put a 1 kilo ohm resistor in series with the wire, and that limits the current. Voltages were all very small. It's not only milliamps but millivolts. I got these results. Graph looks like this. It's a lovely straight line. Third example is a filament lamp. Filament lamps are quite high current devices. They operate at a third of an amp for these little torch bulbs. So I don't have any protective resistor in the circuit. This shows positions of the rheostat that I'm using to control voltage, and you can see the lamp brightness varying. These are the results that I obtained. This is the IV characteristic. This is not an ohmic conductor. The voltage is not proportional to the current. I do not have a straight line and it doesn't go through the origin. The sort of exam questions they ask on filament lamps include show how this lamp does not obey Ohm's law, show that the resistance is 1.4 ohms when the current is 0.02 amps, and explain why R is much larger at large voltages. The first question is graph isn't straight. I is not proportional to V, so it doesn't obey Ohm's law. For the second question, you can notice that the first part of the graph is fairly straight. The current is low. The thing is not very hot. You could see from the photos it didn't come on immediately and give out light. You can calculate an upside down gradient, V over I, and get the resistance. I've actually extended my line a bit. They give you a graph like this, drawing a tangent that follows the straight line of the first bit and then doing a gradient triangle off that is accurate. So here I get a voltage of 0.0563 volts and 0.04 amps, and that gives me a resistance of 1.41 ohms. Finally, they're asking for ideas about larger currents heat up the wire, so the lattice vibrates more. This increases the resistance, so for a given increase in voltage you get a smaller current change. Example 4 is the diode. Diode is a solid state component that only allows current to flow one way. This is an actual diode, and its symbol, conventional current, flows in the direction of the triangle arrow, and the bar corresponds to black line on the diode itself. I've used the 150 ohm resistor that I used for example 1 as a protective in this circuit, and you can see it in this photo. It appears in this circuit diagram. You can see here current flowing in a forward direction, but if I reverse the diode, I get negative voltages and no current flows. Here's the results table. This is the graph. There is no proportionality here. Diodes are not ohmic. The important thing is that they have a turn-on voltage. No conduction occurs until the voltage reaches a minimum value. You're putting enough energy in to overcome the band gap in the diode itself. This silicon diode is absolutely bang typical. It starts to turn on around 0.6 volts, and by 0.7 volts it's on properly. Then the current rises really strongly. You need a protective resistor. The light emitting diode is a special class of diodes. Like diodes, they are one-way flow devices. This photograph shows an LED in close-up. They have two features to tell you which is the lower potential difference side. The minus side has a shorter leg, but the legs often get shortened to fit into circuits, or plastic package has a lip around it and it has a flat bit that you can just see in this photo. That goes towards the minus minus side. You can see that in this circuit, and I've superimposed the circuit diagram on. Here are photos of me getting forward bias, and that as the voltage increases, eventually you hit a turn on voltage. When I reverse the whole thing, it does not conduct under. This is the results table, and this is the current voltage characteristic. You can see it's exactly the same shape as the silicon diode, but the turn on voltage is higher. It's about 1.8 volts. They're non-ohmic and they don't give any conduction at all below a threshold voltage, and then after that, very big increase in current for a small increase in voltage. This graph shows both the silicon diode and the light emitting diode current voltage characteristics plotted on the same graph. Currents here are all in milliamps. You can see that the LED has a higher turn on voltage. They ask exam questions about LEDs. Draw a circuit to obtain a current and voltage graph for an LED or any diode, then ask you to calculate the output of the power supply. To measure the current and voltage characteristic of an LED, you use the circuit that I showed you earlier. What they're really interested in is checking that you know the right places to put an ammeter and a voltmeter. It should show the protective resistor and give it a value somewhere in the range about 100 ohms to 400, 500 ohms. For this circuit, the protective resistance is 150 ohms and the current is 6 milliamp. The resistance is in series with the diode, so the supply voltage is the sum of the resistance voltage and the LED voltage. You can work out the resistance voltage using IR, so 6 times 10 to the minus 3 times 150, and that gives you voltage drop across the resistor of 0.9 volts. LED voltage is read off the graph. Supply voltage of 0.9 plus 1.8 volts. The supply voltage in this case is 2.7 volts. This video has shown the practical ways in which the current voltage graphs of components are obtained, how this knowledge is assessed in exams. Some of these components can be used to sense the environment and control circuits. That's what's covered in part C of this series of